In this video, we're going to continue our discussion of section 4.1. This is preliminary theory for higher order diffie-qs. What we're working on right now is in the past video, we talked about that if I had multiple solutions to a linear differential equation that was homogeneous, however you want to say it, then I could put those functions together, those solutions with constants, and add them together and get a whole new solution. We ended that video with asking, how do I know if there are more solutions? Is every solution based on the solutions that we have? So what we're going to answer first, before we get to that, we have to ask if our solutions are linear dependent or independent. Okay, what this means is dependent is that all solutions can be made from the other solutions. That's like a roundabout way of saying it. All right, all solutions can be made from the other solutions. All right, so that means if uh, it's weird to say it like that, and maybe not solutions here, because we haven't talked about solutions, they just said functions. So their functions, all functions can be made from the other functions. So if they gave me a set of functions, then I know they are linear dependent if they can be made by the other functions. And it's like, what I mean by that is like constant multiples to get the other. Okay, here's a roundabout way of saying this too, and we can think about it. So a set of functions, f1, 2, up to n, is said to be linear dependent on an interval I if there exist constants c1, c2, up through cn that are not all zero, such that when I add those, I can find all these c's that when I add them like that, I get 0. You could think about it this way as well. Think about if I move that c1 over, and then I still have this like big sum here, whatever, however long that may be, and I were to move it over, I'd get negative C1 F1 of X. Do you see what that says is that I can pick all the correct C's over here to make it work. That way, that when I do all of this and I multiply and I add all the functions, I get the other one, right? You pick your function. I can give you the right amount of C's that would give you some kind of C of the other function. Or I could just take the C negative C1 and divide it into the other side, right? If I did negative C1 over here, and that would be gone. So there would be, and I do C2 over negative over C1, that's a new constant. So any constant you pick, you can get that other function. So they're based, another way you can say they're based on each other, right? That they all kind of build to get the same thing. So what you're looking for right now, there's a quicker way to this, unless it's not too complicated. And you'll see, we pick the easy ones up front here. So we're trying to make this happen. This is a better way to look at it. Is there a way to get pick C's that way when I put them in front of my F's, that it's all going to be 0? So take a look. A set of functions they gave us is cosine squared, sine squared, secant squared, and tangent squared. And they want to know, are they linear dependent solutions or are they independent? So we're going to create that statement that was written, C1 times cosine squared of x plus C2 times sine squared of x plus C3 secant squared x plus C4 is tangent squared x. And we're wondering, can you pick the right C's to make that true? If you can, then they are linear dependent, meaning that I can create the other ones from all the others. I can create one from the others. So here, I'm trying to find the C's. Now looking at it, okay, I'm trying to make things, if you haven't kind of picked it up, I need like these to cancel out to get a 0, right? Well, as they stand, if I just pick numbers for these, things don't work out pretty. Like I need to get rid of cosine squared, I need a cosine squared. So I need to do some manipulation. If I need a cosine squared, is there something here I can turn to get a cosine squared? Yeah, I can change sine squared to cosine squared. So I'm going to get C1 times cosine squared x plus C2, and I'm going to change this to 1 minus sine squared x, or cosine squared x. That way, I can just like cancel those out maybe. Okay, the other two, look, I have a tangent and a secant. And if we use how I get to it, sine squared plus cosine squared equals 1. What I do to get to the other ones, if I need to see a tangent, then I'm going to divide everything by cosine squared. And think about it, sine over cosine is tangent. Cosine squared over cosine is 1. And 1 over cosine squared is secant squared. I know that's not the best way to write it, but this is just for my head right now, right? So I'm going to change that secant squared to a tangent squared plus 1. And then C4, I'm going to leave that as a tangent squared. So now to notice with the C's that I'm picking, like I'll have things that should go away or stay. Okay, so if you look right now, if I were to multiply that out, let's multiply out and just think about how if things cancel. Well, if you look that this cosine squared could cancel, if I let C1 equal 1 and C2 equal 1, this cosine and the cosine squared there are going to cancel, and I'm just going to be left with a 1 from that. That's all I'm going to have there. So take a look at that. If you don't believe me, go ahead and plug those in and look. Right, and then the other side, I need that C4 to go away, but I also, okay, so if I did C3 equals 1 and C4 equals -1, notice that the tangents go away, right? But I'm gonna have a positive 1, and 1 plus 1 is not 0. That's not what I want. So instead, what if we were to flip them and put -1 here and a positive 1 here? So that takes care of the tangent still, but now I'm gonna have a -1, and that equals 0, right? So what this means is I found C1, C2, C3, C4 to make that statement true. So F1, F2, F3, and F4, are linearly dependent on each other. I can get the other ones from, you give me 3 of them, I get the other one. This is going to have a special property here in a moment, um, but we'll see when we get there. Okay, so those are linearly dependent. Okay, we're going to do one more here, and then I'll give you guys the trick. Right, because these aren't bad if they're like that. You might have been like, no, that was still terrible. Trig's hard. I get it. That's most of my calc students' opinion. Um, but it's not going to always be easy to find this. And then what if I give you, and the way to do it, I'm going to show you in the next page, isn't going to be much quicker. It's still a long process, but there's a quicker, more like follow your nose way to do this. What I mean by follow your nose way is you don't have to sit there and stare at your C's to try to find it or do some crazy changing. Okay, so I'll move on. Let's do one more here, and then I'll show you the trick. So they want to know, is this F1 through 4, is it linearly dependent? So I'm going to set up my equation. C1 times x, square root of x plus 5 plus C2 times square root of x plus 5x plus C3 times x minus 1 plus C4 times x squared. And we're wondering, can we find C's to make that 0? Well, okay. I see a couple things. I have a big issue with this one. I want you to think about it. There's something on here that just tells me no. And remember, the C's have to be just constants. I can't introduce another variable, can't do anything. They just have to be a number. Could be a fraction, could be pi, could be a number, any constant, but can't be x's. So my issue with looking at it right away, what I see is I see that. And I got to get rid of x squared. Well, there's nothing, I don't think that's going to get rid of that x squared. I can't change any of the x's. I can't change, this isn't the trig stuff above where I can do a full change. Square root of x plus 5 is not equal to anything else. I can't factor it and make it prettier. So there are no c's. So that's not going away here. It's not going away. So what this means is that they are linearly independent. So they cannot be made from each other, as what we just seen. We can't get them to cancel out. Okay, so this is great when the problems are like this. You know, that's not too bad. They're not horrible. It's doable. But if I gave you functions that didn't look so similar and they were big rational functions that didn't add easy or something strange like that, reciprocal functions, inverse trig functions, and trying to find all that, that would be very difficult to figure out. So there's a way around it. I'm going to introduce you to some theory here. We're not going to prove anything. We're just going to take it for its word. The Wronskian, and I'm going to put another theorem in here so you can see it and it's written out. I'm going to add some stuff. So suppose each function's f1 through fn possesses at least n minus 1 derivatives. The determinant, this is a linear algebra thing. So if you need to go look this up, you're going to need to do it. We do it in Calc 3. You do it in physics. You should be for cross products. This is a Calc 3 thing, right? If you need to look, sorry, not Calc 3. We use it in Calc 3. This is a linear algebra thing. So a lot of you guys probably haven't had linear algebra, and that's okay. This is a total something you should be able to do. If you haven't had Calc 3, you're going to need to look into this determinant thing. It is really just an algorithm. It's not going to be anything that you're going to need to go and stare at and try to understand the logic behind it. It's just going to be set up for in a certain way to get there, and I'll show you. So this is called the Wronskian. All right, how we denote the Wronskian, notice they did a W, and then they just put the functions inside, right? And then this thing is going to have a number, and we're only concerned with one number. Okay, this has an algorithm. I'll show you guys how to do that. We're going to do an example here in a moment. But what this says, that if the Wronskian is 0 for all x, uh, uh, yeah, for all x, then f1, f2 through fn are linearly dependent. So if you can get it equal to 0, then you know that it's linearly dependent. If it's not equal to 0, meaning you get a 5x or 13x or sine x or something like that, it's going to be linearly independent. Okay? So why this is important, all right? Any set. So remember, we're talking about solutions of diffie-q's. Remember, we took a little tangent here. The fundamental solutions set of solutions, okay? What this is going to be is this is going to be a set of solutions that become a basis, is a term in vectors and linear algebra. But these solutions can be used to come up with every solution. I almost said any and every, so sorry for that weird word there. But it become any solution to that diffie-q I can create from a linear combination of these solutions. So as long as they are linearly independent. If they are linearly independent, then they are the fundamental set of solutions on the interval. Fundamental set solutions means they're the only solutions. That's it. All other solutions can be made from that set of solutions. Okay. So existence of a fundamental set. There exists a fundamental set of solutions for the homogeneous linear nth order differential equation on the interval I. They exist. All right. So there is a fundamental set. Okay. This fundamental set of solutions creates a general solution. So let's say these are all in solutions of the homogeneous linear, and all those are linearly independent, dependent. If that's true, then this is true. Then the general solution is that. All right. So as long as those are the fundamental set, has to be, I guess you could write here, fundamental set. Has to be the fundamental set. If it is the fundamental set of solutions, then that is the general solution. Remember, what a linear independent solutions, that implies that. right? And linearly independent solutions tells me that I have a fundamental set of solutions, which means this is the general solution. Gives you every solution. All right, so let's put this in practice because some of you guys are like, okay, cool, you said a weird word, Ronskin, you put it in those bars, but I've never seen that before. Let's talk about how to do this. Okay, so they gave us three solutions, right? Here are just functions, and we're trying to determine if they are linearly independent. So the Ronskin, we're going to write W of F1, F2, F3. And then this is how we do it. You're going to start, don't do both bars, just do one bar. And I'm going to put the functions across the top. Here, I'm going to write actually the long way first. F1, F2, and F3. What you do, and then you can close it on this side, straight up and down bars. And we're going to take derivatives of this until we make a square. All right, so F1 derivative, F2, or sorry, F1 double derivative. So you do derivatives going down like that. F2 derivative, F2 double derivative, F3 derivative, F3 double derivative. All right, I just didn't put the X's behind to just really emphasize those primes. So notice I now have a 3 by 3 matrix. All right, so how this algorithm works, all right? I'm gonna shrink this up just a bit. Forgive me. I just have to write small. It's kind of hard to make sure you guys can see it, read it, and me fit it in. So we'll do that. Sorry, you guys. Okay, how this works is we are going to highlight one row. You can pick any one you want, one row and one column. I usually just stick with that unless there are zeros, and I'll show you an example of that in our second example. So what we're gonna do is you can move the rows, you can move the columns, but you got to do it consistently. So first thing I'm going to write, you see how I marked out those? I'm going to put in a smaller determinant, so straight bars again, F2 prime, F2 double prime, and then we're going to do F3 prime, F3 double prime, and then we put its times whatever the intersection was. So do you see how F1 was here? Times. Now, the thing you're going to have to trust me for, this is the linear algebra part. We do minus next. Okay. And then what I'm going to do now is I take the column and I'm going to move it here. You can move either the column or you can move the row. It doesn't matter as long as you consistently just move that one twice. And you'll see what I mean after we move it again. So now I have the part that's not highlighted is going to go into a smaller determinant. That's F1 prime, F1 double prime, F3 prime, F3 double prime. This is times its intersection, which is F2. Okay, we have one more to make here. I'm just gonna put it right below. I should have wrote smaller, forgive me. And what I do now is how I move the row, right? I moved the row, so the next thing I'm gonna do is move my row again. You might just want to lightly mark them. I said it backwards. Lightly mark them, or however you want to do it. Put your pencil down on it, something. So now I'm going to write what's left there. I get F1 prime, F1 double prime, F2 prime, F2 double prime, and then I'm going to times that by F3. That is what the first step is. Okay, the next step for determinant, and then this is where it gets easier. I'm going to go ahead and let's go ahead and fill in each part of that. All right, so if I do that, I'm going to go ahead and F2 prime here. Okay, so let's go ahead and do that. F1 is 0, so F1 prime is 0, F1 double prime, 0. F2 is X, so F2 prime is 1, F2 double prime is 0. F3 is e to the X, so F3 prime is e to the X, and F3 double prime is e to the x. So we'll fill all those in. Okay, f2 prime is 1, f2 double prime is 0, f3 prime is e to the x, and then e to the x, times f1, which is 0. That's convenient. And then the next part, we'll do f1 prime, which is 0, 0, and then f3 prime is e to the x, e to the x. I'm just grabbing each one times f2, which is x, plus, and then our last one, okay, is f1 prime, so 0, f2, f1 double prime. f2 prime is 1, and then an e to the x, and this will be times f3, and f3 was e to the x. Okay, our last step here, and this is how we get down to our answer, okay, promise. Determinant, a 2 by 2 determinant. How we do a 2 by 2? A 3 by 3 is what I just did. That turns into this. Forgive me for this weird ant there. Now I'm going to take this diagonal, I multiply that, and then I'm going to minus the multiplication of that. Meaning, okay, so I got 1 times e to the x minus e to the x times 0 times the 0 up front. So I didn't really need to do it there, but I'm teaching you guys how it goes. And then here the same thing, 0 times e to the x is 0 minus 0 times e to the x is 0. And that's just times x. And then plus this last one is going to be 0 times e to the x, which is 0, minus 1 times 0 is 0. And all that's times e to the x. Well, all of that is 0. So since that is 0, that means they are dependent, linearly dependent, because it was 0. Right. This will get easier with time. Also, we'll be able to skip this whole step right here. I'll show you in this next example. We don't need to write it out like that. We can just fill in the original determinant, the original Wronskian, and run through it. It'll be much quicker. Once you guys do a handful of these, I know it says the professor in the room, but once you guys do a handful of these get pretty quick. All right, so let's do this next one. It won't take as much room. So the Wronskian of F1, F2, you could fill these in if you wanted to with their actual names. I wouldn't because I'm lazy. And now what I'm going to fill in here, and this is, I don't do any of these that I did up here. I don't write any of that. I'm just going to go ahead and do my cosine of 2x. And then I know to fill in the rest, I'm just going to take a derivative going down. So it's negative 2 sine 2x, and then negative 4 cosine 2x. So that's the derivative and the derivative again. F2 is 1, 0, 0. Okay, and then cosine squared is a chain rule. Okay, I'm going to bring the 2 down. There's a cosine, and then I times by the derivative of cosine, which is a negative sine. Horrible, right? Okay, and then the last one here, unfortunately, it is a product rule. So I'm going to leave, okay, I keep a negative 2. I'll do sine first. Sine is cosine squared, or it'll be cosine, so I get a cosine squared. And then I know I'm going to introduce a I'll keep the negative, and now I got to do the derivative of cosine, which is going to produce a positive. That's where I was going. So now it's going to be a sine squared, but that 2 is still there. That is just the product rule. If you need to slow down, write it out, please do. All right, we could actually change some of these. This is gonna be some of your trig stuff. This kind of thing, I'll just give to you on an exam, like some of these difficult, real difficult ones. It'd be best if you could memorize for future stuff. That way you're aware of where things are. But you don't have to. Okay, so this is cosine 2x. This is negative 2 sine 2x. Nothing changes. I'm gonna fit this all in here. No, I'm not. Okay, what I'm gonna do instead of that is I'm gonna write down what they simplify down to in red right underneath. Okay, this first thing here is just a sine 2x, a negative sine 2x. All right, down below is actually a negative 2 cosine 2x. Right, if you don't believe me, go look up at your trig table. We get cosine squared minus sine squared. So if I factor out negative 2, that's cosine 2x. All right, so take my word for it or look it up. The thing about trig functions, my opinion, I know I have colleagues that are like, no, you need to memorize, and I have colleagues that are like, no, you could just look things up, and that's the end of their opinion. Mine's in the middle. you got to be able to tell that that is a trig function. Do you need to know what exactly, like a trig identity? Sorry. Do you need to know exactly what it is? No, but you would need to know. Okay, I need to go look that up. Does that help with an exam? No, but exams are just for school. If you're using this stuff out in the real world, if that ends up being you, then you need to know it exists and then you can look it up, right? But if you don't even know that 2 cosine sine x is something, then how do you even know to go look it up? Okay, I'll get off that box. But so you need in the middle, right? Some memorization, some familiarity, I think is better. Okay, here is, I was trying to emphasize this on the problem above. I can pick any row. So I'm gonna pick this row and then any column I want. All right, so I'm gonna pick that column. You could probably guess why I'm picking that column. All right, so what I'm gonna do is now, instead of moving the column, I'm gonna take this row and move it down twice, right? I'm gonna do that twice. So the first row, I mark down what's left. -2 sine 2x, -4 cosine 2x, uh, negative sine 2x, and -2 cosine 2x. But it doesn't matter because that's times the intersection. Oh, it does matter in this one, times 1. Okay, I got to teach you something that's going to be like you're gonna have to trust me for it. When I'm doing these and I'm doing the determinant, you have to follow. Over a second ago, I had you guys put this like random negative up here, right? Random negative. It comes from this. On your intersections, you have to use these signs: plus, negative, plus, negative, plus, negative, plus, negative, plus. So only the intersections. So this being a +1 or a 1 there, well, if I go look at the chart I just wrote out there, I know I need to put not just 1, I need to put -1. All right. The next one, okay, so I'm going to erase that. I take the row and I'm going to move it down so I can use these zeros. Okay, so now I know I'm going to use the inside there cosine 2x, cosine squared x, -4 cosine 2x, -2 cosine 2x. But this is times 0, right? That's the intersection. Okay, and then I know now I'm going to delete my row, go down one more, and then maybe you guys can see this now. That's going to be a minus because that's where the intersection is, or I could have kept it behind. It doesn't matter what's in here because I'm going to times by 0. Okay, so you could put all that in, but I know I'm going to multiply by 0. I also know that this is times 0, so that's gone. So both of those are gone. So the only thing that's there is that first part. All right. So it comes down to, if it's 0, then we're good. It's going to be linearly dependent. But if it's not 0, then it's the independent. Okay, so if I multiply, I get 4. I'm just going to put it up here. 4 sine 2x, cosine 2x, and then multiply. The two negatives make a positive, but it's a minus, and that's going to be -4 sine 2x, cosine 2x. So it actually makes a 0, which means that they are linearly dependent. If you get anything other than 0, they're linearly independent. Okay, we got one more here, and then we'll end the video here and move on to another idea. Okay, given the set of functions, we're trying to figure out if they are linearly independent. So we're going to do a Wronskian again of f1, f2, f3. Like I said, you could put the functions right there, but I like doing that because, like I said, I'm lazy. All right, so remember, we write our functions across the top: e to the x, e to the negative x, and then that is hyperbolic sine. That's not a typo. This is like doing trigonometry on the inside of a sphere. This is going to be probably some heavy stuff if any of you guys are interested in astrophysics, with our recent observations that we potentially are inside of a black hole, which means trig would work maybe on the inside of a sphere type thing. We never know. But these are interesting. There are whole fields based on, I took a class based on hyperbolic trig. It was very interesting. I'll end there. All right, so I just need to make a square. So that means I'm going to go down. These are derivatives. Okay, so e to the x, e to the x, e to the x. Then I'm going to get negative e to the x, negative e to the negative x, and then I get a positive negative e to the negative x because they would introduce another negative. Now, you might not have these memorized. They're really easy. Sinh is the way they say that. Hyperbolic sine derivative is hyperbolic cosine. And then this is the dream. Hyperbolic cosine is hyperbolic sine. There's no negative. That's just how it works. Okay. I think looking here, we should probably go down this row, and I'm going to move the row down. Okay, so let's give it a shot. Create your first one. I got negative e to the negative x, cosh x, and then I got e to the negative x, hyperbolic sine or sinh, I guess, and then I times it by its intersection. That's a plus, right? Now I know this next one, if I move it down, this one's going to be a minus because of the intersection and where it's at. So I'm going to minus, and then I got e to the negative x, e to the negative x, and I'm going to get sinh, hyperbolic sine, and hyperbolic sine, and then times e to the x plus, and then it's our last one here. Cover that up. I write down what's inside there, e to the negative x, negative e to the negative x, sinh, or hyperbolic cosh, and then all this is times e to the x. Okay. All right, I'm going to add a page so I don't feel cramped. If it'll let me. Go. Okay, so going over here to make sure I have plenty of room. Okay, I got negative e to the negative x times sinh x, and then it's going to be minus e to the negative x cosh x times e to the x minus e to the negative x sinh x minus e to the negative x sinh x times e to the x. And then our last one, I got to go down. E to the negative x cosh. And then this is going to be a plus e to the negative x sinh times e to the x. Okay, so we get not a lot of things are going to go away. Let's see what's going to happen here. I think I might have chosen the worst way to do it, which is awesome. So we got it, not really, it's just my notes. I chose a much simpler way. E to the x goes there, and those e to the x's are going to go away, and I'm going to get a negative sinh of x. Make sure you're putting x's on there. And then if I multiply, I get the same thing goes away, and I get negative cosh x. Okay, minus. The e to the x's are all going to go away here, and I'm going to get minus sinh x, and then plus sinh. Actually, let's not do it that way. Look, these just go away. Oh, they're the same. All right, those are gone, so a 0. Guess we could do minus 0 plus. And then the same thing here, those x's are going away, leaving me with cosh x plus sinh x. And we got the negatives there resulting in a 0, which means that they are linearly dependent. We are going to be looking in the next videos for linear independence, but it's easier to just to show the 0 because now you know if you get anything other than 0, it's linearly independent, which is going to imply something that we're going to look at in our next video.